So he is now in the professor Julian laboratory. The part of his talk is 2D smoothing based recursive subspace and factor framework for high mobility geolocation and tracking with a duality consideration to join to Delay-Doppler. Yeah, can you make it full screen? Okay. Okay. The next talk is about 30 minutes, but consider roughly, not strict. Yeah.
Okay. So good afternoon, everyone. My name is Lei Jiang. Now I'm a PhD student belonging to Department of Transdisciplinary Science and Technology, Tokyo Institute of Technology. So I think this is the last time I use the name Tokyo Institute of Technology. So the last time, because the next month the school name will become the Science Tokyo. So today I'm going to share my current research work, which is the 2D smoothing-based recursive subspace and the background framework for high mobility geolocation and tracking. And also I want to give some introduction about our proposed technique applied to the joint delay and Doppler estimation, maybe in the future work. So this is the outline for today's presentation. I will give a background first. Then I will give a detailed introduction about our proposed 2D smoothing technique for DO estimation and tracking. And then I will introduce another part of our work, which is related to the photograph-based geolocation and tracking. So the background of our project is focusing on the commercial aviation geolocation, because the traffic demand of the aviation is decreasing within the 13 years, especially after the COVID-19. So to manage the safety and the efficiency of the commercial aviation, we need to, propose a more efficient aircraft geolocation and navigation system. So in general, from the viewpoint of the application, there are two types of geolocation. One is called the self-targeted geolocation, including the GNSS system and the INS systems. However, these systems suffers from some limitations. For example, the GNSS system suffers from the atmospheric effects, and also the INS systems, they will cause some cumulative error to affect the final estimation results. And one more important thing is that the target of the airplane needs to be identified in advance. And the second geolocation application is called the external target geolocation. So in this application, we use the ground-based radar to detect the signal sent from the airplane, and use the signal and use the received signal to estimate the target position. So in this case, this application can achieve more robustness compared with the self-targeted geolocation technique. And also one important thing is that the target can be anonymous. That means not only the commercial aviation airplanes, but also some private airplanes can be also estimated and tracked. And from the viewpoint of the technology, there are two types also. One is called the translation technique, which we measure the distance between the target and the sensors. And then we can estimate the intersection point to determine the final position of the target. However, in this technique, we need to necessitate the time synchronization, not only among the sensors, but also between the sensors and the targets. That means we have to achieve the perfect system level synchronization which is very difficult in practical because this perfect system level needs a lot of effort to be satisfied. And another technique is called the triangulation method, which we measure the angles between the targets and the sensors instead of the distance. So in this technique, we only need to satisfy the sensor level synchronization. That means the time synchronization only needs to be satisfied among the sensors, not between the sensor and the target. So compared to the triangulation method, this technique is is easier to be realized. So compared with so in our project, we focus on the triangulation-based method, which we need to estimate the angles first, which is the direction of arrival. So there's a conventional technique called the subspace technique, which can be used to estimate the angle information first. So the traditional subspace-based method is using the array geometry to achieve the signal, to achieve the received signal like this, and then we can calculate the covariance matrix like this. So the next thing is we conduct the block-wise eigenvalue decomposition of this covariance matrix calculated from the received signal to separate the signal subspace and the noise subspace. Then we can use some subspace technique to find the DO estimation from the signal subspace or the noise subspace. However, this conventional subspace technique suffers from some challenges. One is the coherent signal and the rank deficiency. Since the target we are dealing with is the L plane with the high mobility, with the narrowband signal. So in this case, the coherent multipath is inherently exists in the received signal model. That means the multipath signal shares the similar characters such as the frequency or the angles, which will cause the correlated entries in the covariance matrix. So in this case, if we use this rank deficient covariance matrix to conduct the eigenvalue decomposition, we can lose some source compared to the full rank covariance matrix, for example, like this. So in this case, if the covariance matrix is full rank, then we can get the signal subspace and the noise subspace like this. However, if the covariance matrix is with deficient rank, then we can see there's one signal subspace fallen into the noise subspace, which means we lose some signal source. And another challenge is the empirical non-stationarity in the model. Because due to the high mobility, we can only have the finite samples or the finite measurement duration to avoid the angle changes. So in this case, we can only have the finite samples. For example, in the right figure, we can see that the conventional subspace technique will require all of these samples to get the covariance matrix and conduct the subspace to estimate the DOA. However, in our scenario, we can only have part of the samples like this. So this part of samples cannot cover the whole property of the signal model. So in this case, the conventional subspace technique may provide the inaccurate estimation results. So to solve these two challenges, we propose the recursive subspace and backgraph framework. The whole framework includes two parts. One is for the DO estimation and tracking. And the second part is that we use the estimate the angle information to estimate the target position and track it. So first, I'm going to introduce the part one. So in conventional way to solve the rank deficiency, normally we can conduct the conventional spatial smoothing. So this technique first separates all of the elements in the spatial domain into several sub-areas, and then we can calculate the covariance matrix at each sub-area and then take the average. So this technique can somehow decorrelate the coherence, but it relies on two characters. One is the number of the subarray, the number of the subarray. If the number of the subarray is huge, then we can get the perfect decorrelation performance. But in practical, it's hard to construct the large size of array due to the financial cost. And another characteristic is relying on the directional sign of the DOA difference, which is related here. So if these values are very small between the two paths, then this coefficient is also very small, which means the decorrelation performance is limited. So to solve these limitations in the conventional spatial smoothing, one potential solution is called the temporal smoothing. So instead of we separate the subarrays in spatial domain, we separate the snapshots in time domain, and we can conduct the same process as we did in the spatial domain. So in this case, the performance now is relying on these coefficients. It's determined by the number of the sub-snapshot and the number of the Doppler difference. However, this technique also suffers from some limitations. For example, the finite samples due to the empirical non-stationarity, as I introduced, due to the high mobility, and also the small Doppler difference will also cause have a bad impact on the decorrelation performance. So to combine these limitations from the 1D smoothing technique, we proposed a 2D smoothing technique by combining the spatial domain and the time domain together. So in this case, we separate the snapshot into several sub-rectangular, both in spatial domain and in time domain. And then we conduct the smoothing procedure from the beginning to the end. So in this case, the performance is relying on these coefficients. We can see that it's the product by the coefficient in the spatial smoothing and the coefficient in the temporal smoothing. So in this case, we can fully utilize the array element and the finite samples to decorrelate the coherence. And also, the decorrelation performance is improved even in the small DSD or the Doppler difference area. But this proposed technique also faces some challenges. For example, it can only apply for the static DOA estimation. Because, I mean, when we want to track the targets, this static DOA estimation will have some side effects on the tracking performance. And also, because we combine the spatial domain and the time domain together, we have to conduct the extra smoothing efforts in the size of the, for example, Mn times Mn covariance matrix. That means that this covariance matrix size becomes larger. It requires the extra computation efforts. So to solve these limitations, we further improve our technique into a recursive way. That means we convert the blockwise into the recursive by first we separate the snapshots into several segments, and we only conduct the smoothing at the first segment, and then we can use the previous message plus the new observation to update this smooth covariance matrix to realize the recursive way. So by doing this, we can improve the accuracy by the iteration procedure, and also we can reduce the computation efforts by smoothing in the size, now it's in the size like this. And one more important thing is that we can provide the fundamental condition for the DOA tracking, because the covariance matrix now can be tracked. So the DOA can be tracked as well. So to realize DOA tracking, we need to track the subspace. So there's a typical way, which is called the low rank adaptive filter, can be applied for tracking the subspace technique. So we first use the proposed recursive 2D smoothing to update the covariance matrix. And then we combine the low rank algorithm to track the subspace. And finally, we can track the DOA. So next, I want to connect our project to the joint delay Doppler estimation, because we can consider the joint delay-Doppler estimation is the duality in the orthogonal time frequency space modulation scheme. So if we use the delay-Doppler to represent the signal model, it can be shown like this. And this term, S is the transmit signal. It contains the delay information, and also this one is related to the Doppler information. So we can extract the OTFS channels by using this delay-Doppler domain, given like this. So we can see that this term is related to delay, and this term is related to Doppler. So what we are thinking about is, can we apply our 2D smoothing technique to combine these two domains, I mean the delay domain and the Doppler domain together, to joint estimate the delay and the Doppler by using the subspace technique we proposed. So let's analyze this property of the OTF channels. So first, if we use the sensors to receive the frequency, to receive the signal in frequency and the time domain, and we can conduct the symplectic Fourier transform to transform this frequency time channel response to the delay Doppler channel response, for example, like this. However, we can think about this. If the target is with high mobility, that means the large Doppler shift we can get. And another thing is that the finite samples in the time domain is also limited in this technique. Even though we conducted the SFT transform, then we can get the finite samples in delay Doppler domain. That means this empirical non-stationarity is also exists in the OTFS channels. So to solve these problems, we think about we can also apply our 2D smoothing technique to this joint delay Doppler estimation under the empirical non-stationary environments. So the connection is like this. So this is our received signal model. If we use the vector form to represent it, we can say that this vector A represents the DOA information, and the steering vector S represents the Doppler information. And also we use the same vector form to represent this signal model. We can find the similar representation. So this steering vector represents the Doppler and the S represents the delay. So in our case, actually we combine the time domain and the spatial domain together by using the vectorization operation, which is called the vector operation. That means we combine the spatial domain, which is related to the DOA, and the Doppler domain, which is related to the time domain, together like this. And these two domains can be combined by this chronic product. So we think about maybe this technique can be applied to this OTFS channel. For example, like this. We use the vector operation to combine the delay and Doppler into one combined domain. And this actually has some difference with the previous one. So in previous OTFS channel, we can find that this, channel model H represents actually is the two independent domain multiplication like this, right? However, in our case, it's not two independent multiplication. It's the vector operation to combine these two domains by this chronic product. They are different. So by doing this, we can fully use the samples in two domains, and also we can use the subspace technique to joint estimate the delay and the Doppler. So this is the connection between our project and this OTFS channel. Maybe we will conduct this research in the future. So let's get more clearly. So the up figure shows the 2D smoothing in our scenario. So we combine the spatial domain and the timing domain together. We first conducted the 2D smoothing, and then we use the subspace method to extract the DOA and the Doppler information in DOA domain and the Doppler domain. So this dot actually is related to the eigenvalues by using this subspace technique. So from this flow, we can jointly estimate the DOA and the Doppler. So similarly, we can combine the frequency domain and the time domain together and conducted 2D smoothing to solve the coherency under the empirical non-stationary environment. And then we can conduct a subspace method to extract the eigenvalues related to the delay and the Doppler to jointly estimate the delay and the Doppler. So this is the strategy of the 2D smoothing can be applied to the OTFS channel. So next, I'm going to introduce the second part of our framework, which is related to the geolocation and tracking. We know that if we use the triangulation method, we have to solve this nonlinear multivariable problem. Actually, directly solving is very difficult. So we first conduct the first order Taylor series to linearize it. Then we can get the information related to the target position. So based on this position information, we can construct the fact graph like this. So this fact graph is for geolocation. So first we can input the estimated DOA by the recursive subspace technique, and then we can conduct the iteration process between the compression node and the estimation node until the convergence we achieve. Then we output the target position information. So this information is the fine estimate of the current position. So next, we want to realize the tracking purpose. We have to combine some technique, for example, the extended Kalman filter to realize the tracking purpose. So actually, this one is the whole tracking fact graph. So first, we can estimate the prediction state from the previous one, and then we can use this information from the FEGE as the observation state to refine this prediction to get the fine estimate of the current state. And this level represents the position information update, and this level represents the speed, and this one represents the acceleration. So in this whole framework, not only the position state can be estimated and updated, but also the velocity and the acceleration. So by combining these two parameters together, I mean dynamically estimation and update together, we can get a stable framework. So actually, I'm going to show some simulation results. So to create a simulation scenario, we first will consider about the two-pass model, which we use the ground-to-air communication systems. And we use the signal model, which is very high frequency. So in our simulation, we define the 150 megahertz, and we assume the detection range of the air to ground sensors is up to the 320 kilometers. And we consider about the bias, the speed of the aviation is about the 200 meters per second. And also we set the parameters for the two-pass signal model. From the signal model under the rank, under the analysis of the covariance matrix, we can find that the rank is determined by these two values. One, we call it the normalized Doppler difference, and another is the normalized DCD difference. So first, we want to create a non-stationary environment. So first, we conduct the spatial smoothing and the temporal smoothing. We found that each conventional smoothing technique suffers from the small normalized DS difference or the small normalized Doppler difference. And then we conduct the 2D smoothing. We find that this limited area is decreasing sharply. And then we can define this area to simulate the non-stationary environment by choosing these two parameters, by setting these two parameters like this. And then we design a trajectory model of the airplane for the DOA tracking. So we consider about the nonlinear trajectory like this, and the angular velocity is fixed. And also we think about the random duration of the trajectory like this. So first, I'm going to show some DOA tracking results. So the left figure shows the DOA tracking result because we are using because we use the two-pass model. So there are two DOA we want to track. we can see that the red line is the true values, and the blue line is related to the estimated values by our proposed technique. We can find the gap between two of them are very small, illustrating the high tracking accuracy of the DOA. And also we calculate the RMC of the DOA tracking via the different SNRs. We can see that even in this small SNR case, we can track it accurately. And for geolocation, we use the same trajectory like this. So we can find that the proposed framework can dynamically track the targeted trajectory with the high mobility, even with the high mobility. And we analyze the accuracy by calculating the RMSE of the tracking. So I'm going to make a summary of today's presentation. So first is we want to design a geolocation and a tracking system to accurately estimate and tracking aircraft position and provide the redundancy in current existing navigation system. So we proposed a distributed sensor-based geolocation and the tracking framework, which we call it the recursive. And this technique can jointly estimate the DOA and the location of the fast-moving target, like the airplane. And this approach can improve the robustness by adjusting the distribution plate flexibly to fit the large range of the applications. And the next objective is to decorrelate the coherent multipath in empirical non-stationarity. So we first analyze what is the empirical non-stationarity, and then we propose the blockwise and the recursive to this smoothing technique to decorrelate the coherency to solve the challenge due to this empirical non-stationarity. So this approach is proposed to decorrelate coherent multipath under empirical non-stationarity under non-stationary environment, and further realize the subspace tracking of the fast-moving target by this recursive form. So actually, there's another objective is we want to combine, or also we want to apply our recursive to this smoothing technique into the OTFF channels to jointly estimate the delay and the Doppler, which may provide a new potential solution compared with the conventional techniques. So that's all of my presentation. Thank you for your attention.
Open for questions. You have any questions? Okay. About page probably 17. So thank you for considering the data estimation. Maybe you originally considered the DOA program in the you applied
yeah.
And so the last one is I couldn't understand.
Okay.
You said that these days are defined.
Yes.
So could you explain again?
Okay. Yeah, actually this one is the conventional OTF channel, right? It's the multiplication of the delay domain and the Doppler domain. So this is the two independent domains multiplied with each other, right? However, actually here we can see that this is actually the spin vector. The spin vector we use the vector operation, which means this mu and the tau, they are not independent, they are correlated by using this vector operation, because this is actually the two domains combined by the quantity product, not the simple multiplication. So actually this is the essential difference between this conventional OTF channel and our maybe our potential proposed technique that is in vector.
Let me check that my understanding is correct one. So the capital A equals tau is a vectorization of the compound, then over something, and then they are just multiple Kronecker product.
Yes.
So that this does cannot express this.
Yes.
So that's why I want to first think that the first equation in 5G, yeah, that's right. Because the tau index of tau is L and the index of mu is K.
Yeah.
So this doesn't match with this.
This
The index is only L, but there are two indexes.
Okay, sorry. I think the one step. Actually, this vector form is combining the L and the K. Then we can get this one actually. And this one actually is related to the this one actually.
Yeah, so I think I always use the left
one. Yeah.
Not the right.
I'm not right. I'm not the left one.
Not right one. No. I'm using right hand side. Right. Yes.
Yeah, this one.
Yeah.
Actually, as I mentioned, this one is the kind of the receiver signal by representing delay and Doppler. It has a multipath, so there's the L path, and the K actually is the K Doppler shape. And the right one actually is the OTF channels. We extract this term to represent this channel model. Okay.
Channel in Doppler and delay domain.
Yeah. Actually, I represent this one actually to connect this signal model with our signal model. Okay. So another question.
The basic idea is that in array case, the plane wave coming here, but then it observes that all the phase shift among elements, which means that the spatial frequency. And the spatial frequency is replaced by real frequency. That's what he meant. And that's the reason why we cannot take his word and OTF FS channel model. They are dual.
Okay, great. And then I could one short question about the page 21.
21.
Yeah, just
Okay.
what is the meaning of the equal in that box?
Equal. Actually, this one. Equal means they use the same function. You see. So this actually is the function from the extended constant filter. We use this function first to estimate, to get to the prediction state from the previous state, and this is the feedback from here, from the speed. So that means, actually I can.
I don't know the meaning of the equal.
The equal actually is the same. This one can be put here. They use the same prediction function. But we do not say it's the prediction function because here actually is the refinement. Perfect.
Same mean.
Okay.
Because there are two inputs and one output, right?
Yeah.
So why I can
Okay. Because inside the graph, we only exchange and update the Gaussian message, which is the mean and variance. So here actually it's all of these are scalar values. So for example, for here and here, there are two inputs, right? We first use these two input to get the covariance message, and then we use the covariance message to get the mean message. And this one also is the same. There's one input here and one input here. We use the same update to update the covariance and the mean. Thank you.
So any other questions? Okay, thanks, Gary.